All right, I left the chat on the other window, on the other PC, so we can actually like, so if somebody has any questions, feel free to write them down. I'm gonna actually see them on the other screen. Okay. All right. So today we're gonna cover the divide and conquer algorithms. There are many, but we're gonna pick up the infamous ones, which is merge sort and quick sort. So we're gonna start with merge sort, and divide and conquer is a concept you can see in warfare and other maybe other fields as well, where you take a problem, you divide it into its smaller or the smallest pieces possible, and then you tackle them one by one. This is basically divide and conquer means. Conquer means like attack or kao napad na bosanskom, ajmo reći tako, jel? So so people actually have borrowed this concept, and then they said, okay, let's actually, like, whenever we have a problem, we like in at least in sorting, for example, or in some other algorithms, we just take our problems and then we subdivide them into the smallest pieces possible. And it actually should be like kind of a, I think it should be kind of a habit for you as well. Like when you have a bigger problem, you just simply take it, subdivide it until you solve it. Now, merge sort has two concepts. One of them is the merging itself. The other one is the sorting, for example, right? Now I'm gonna actually go backwards, so it will be much easier for us to. It will be very easy for us to figure out the sorting, because once you know how to merge, sorting is right now is almost solved. So I'm gonna talk about merge sort here. And part one is actually merging. Okay. So given given two sorted arrays, A and B, if I give you two sorted arrays, and they have to be sorted, by the way, there's no other way. I would like actually to merge them into a single array. Okay. Merging them will be as follows. So let's say that you have an array A and an array B. Array A has, for example, 2, 8, 15, 18. Array B has 5, 9, 12, 17, for example. Okay? Now let's say you would like to merge these two arrays into a result array, which is array C. Okay? So how we do that? What we do is we just simply grab two, let's say, pointers or counters, you would like to call them. So I will actually grab different colors here. So this is I, and this is J, for example. Okay. let's say that I and j are actually pointing to the first numbers in the arrays. So the first thing is, if I'm actually sorting this ascending, so from the smallest to the largest, what I'm going to do is I'm going to say, okay, who is actually smallest among I or j, right? So this element is smaller than this element, right? So I'm going to write it, whoops, sorry. So I'm going to write it down. So I'm going to write 2 here and I plus plus. Okay. Coming up next, I is less than j or the opposite. J is less than I, right? So 5 is less than 8, so we write down 5. You increment j. In this case, I is less than j, right? So 8 less than 9, so we write down 8, and we increment the I. Right now, j is larger, is less than I, so we actually put in 9, and we increment j. Then we see j is less than I again, so we actually put in the 12, and we increment j. J, actually, I is less than j, so we put 15. We increment I. J is actually less than I, we put in here, and we increment j, j goes out of the way. This array B is done, so we don't look at this anymore. So this guy is done. And then if you have, for example, I is larger than array A is larger than array B, what you will do is just simply like transfer automatically the whole array, the rest of the array, you can transfer it immediately to C without any comparison because there is only 2 of them, right? So if this is done, no need to compare anything. You just simply push in all the numbers that are left. So if there was like 20, 22, 40 or something like that, there is no need to compare. You just simply like grab everything and just simply plug it in the bottom, right? So this is how to merge two arrays in general. It's very easy, very straightforward. There's nothing fancy about it, right? So what happens if you have a little bit more arrays? So for example, how can you actually do merging? Okay. Now, before actually I go there, if the just let's mention the complexity of this thing. So if the arrays both of the arrays are sorted, if both arrays are sorted, the complexity of this is O of M plus N. M and N are actually the two arrays which you are actually merging. Okay, so in this case it's going to be A and B. Okay, because you are just simply like running through both of the arrays. So the worst case scenario, I mean not the worst case scenario, you're going to always pass through the whole array. And if it is, let's say, 4 arrays or 5 arrays, then you can have M plus N plus X, Y, and Z, and so on and so forth. Now, let's talk about what happens if you have more of them, merging more than 2 lists. And it's also similar. It's also easy, nothing fancy. So let's say you have an array A, array B, array C, D, and you would like to merge it in result R. So let's say you are like having these four arrays and they would like to make a one gigantic array which merged everybody in there. And I will actually make it a little bit smaller. So I'm going to have 4, 6, 12. So we will not run, so we will take eternity. Just we are trying to prove a point here. So let me just draw a line. 3, 5, 9. And we have 8, 10, and 16. And for array D, we have 2, 4, and 18. All right. So what do you usually do? You compare everybody, right? So you have here I, J. Let me write it with different colors so we don't confuse ourselves too much. So this is I, J, K, and let's say L. Okay. And right now you compare the indices. You say who is actually smallest among these four numbers? And the smallest is actually 2. So we're going to put 2. And you increment the L. Okay. Now, you have four numbers to compare. So 4, 3, 8, and 4, right? The smallest is 3. So you put down the 3. And you increment J. Okay. Oops. Sorry. You increment J. Now, we compare 4, 5, 8, 4. Now, we have actually two numbers in there. Now, if you're actually doing this on paper, it's totally fine. You can just simply pick up whatever number you would like to put. Just put one of them. So I'm just going to put 4. But in general, whoop, wow. Did it crash on me? Nope, didn't, sorry. So, but in general, here we go. The merge sort is, I think it was a stable algorithm. I will talk about very stable sorting versus unstable sorting in a minute. But anyway, so we picked up actually the 4, which is actually belonging to the I. So I is going to be incremented right now. And again, when we look at this 6, 5, 8, 4, so right now we pick up the second 4 and we increment the L, right? And then right now we look at this. So 6, 5, 8, 18. So 5 is actually the smallest. So I'm going to have, that's a very weird 4. And 5 is the smallest. I'm going to have it here, increment the J. And then we have 6, 9, 8, 18. So we're going to pick up the 6. And we increment I. And so on and so forth, right? So 12, 9, 8, 18. So K gets incremented. So 8 right now gets into the play. I wonder what's with me today and me erasing things which shouldn't be erased. Okay. All right. So 12, 9, 10, 18. So J increments it. And then so 9 here and J is done. So this is part, this array is done. I don't look at it anymore. Right now I'm actually doing a three-way merge. So 12, 10, and 18. So 10 goes in. We move on. Right? And so on and so forth. So right now you just simply go ahead and plug in the rest of the numbers. There is no need to go really further more than that, but you get the idea. This is called a four-way merge. The above one is called two-way merge. So this guy, so we have, this is called two-way merge. And there are actually, obviously, if you are having more than, more than whatever number you would like to put, you can just simply like put them under the umbrella term, which is n-way merging. I will just simply like put it here for n-way merging. Okay. As simple as that. There's nothing complicated about it. So let's talk about techniques of merging. So if you have a bunch of arrays, so you have A, B, C, and D, you can actually, hang on, let me write this with white. Okay, you can actually merge it that way, so you can have it like so, and then and you merge it into result array. So this is the result array at the end. So result 1, result 2, and then you have result 3. Okay. You can have a another B, C, and D, and you can have it like this. So you merge A and B first, and then you put the result 1, and then you take that result 1 and merge it with C, and then you take the result 2 and you merge it with D, which gives you another result array, which is the final array. Okay. You can actually do the opposite. So also A, B, C, and D, you can do exactly the same thing. So you have R1, R2, and R3, and these are merging techniques. So let me just put the line here. All of them are valid. And it works just fine. Okay. The cool thing about merge sort that merge sort can be actually can be actually distributed. So you can actually send a bunch of machines to actually merge stuff. Like you can actually sort the actual array into multiple machines at the same time on a network, because at the end of the day you can actually let one machine to do A and B merging and another machine do C and D merging, and then once they are done they just simply report back to the server and then they merge stuff. So you can actually do this distributed computing thing if you want to. So now this is actually out of the way. Let's talk about merge sort itself. So right now we know how to merge arrays, right? And you will not believe how simple it is. So I'm going to talk about two-way merge sort, because this is a very Blackboard friendly sorting algorithm. So oh man, what's going on? Two-way merge sort. Okay. Now assume that you have an array that looks like this: 9, 3, 7, 5, 6, 4, 8, and 2. So assume that you have something like this, and you would like to perform a merge sort. The first thing you have to assume is that each one of these elements is a list on its own. Okay? So imagine that you are looking at this array as a list of elements. So array of arrays. So this is an array of one element. There's an array of another element. There's an array of one element. There's an array of one element, and so on and so forth. Imagine that you are having something like this. Okay? So you don't have just a single array. You have like 1, 2, 3, 4, 5, 6, 7, 8. You have 8 arrays. Okay. And what you usually do, you just simply like assume that everyone, because everyone is one element array, that means it actually has been sorted. Right? So what do? We merge. So because this is only a single element in an array, so basically speaking, it's a sorted array because there's only one element in there, so there is nothing to sort. It is actually sorted. It is actually in its position. So because there are actually like 8 lists, right now we're going to merge them. So how do we merge? We merge exactly the same using the same technique we merged upstairs. So we just simply say, aha, okay, these two guys will be merged into a list So we pick up the 3 first in the same way we did above, and 9 next. And right now we have a list of 2 elements. And then we pick up this 2, these 2, and then again we get merged. Actually, there's no need to put them way farther like this because apparently there's a space. I thought I will not have one, so okay. Oh boy, hang on. Trying to make this as neat as possible so we don't confuse ourselves too much. So this is 3, this is 9, this is 5, this is 7, this is 4, and this is 6, right? And then this is 2 and 8. I did just two-way merging and nothing more. So what happens if I had an odd element, right? What happens if I had, for example, 1 here, right? What you usually do is just you simply leave it until the end. And that's it, right? Sorry, you leave it just until the end, and then you merge it later if you had odd number of elements in a two-way merging algorithm. All right, so right now it's actually fairly easy from here on out. So you can actually take these 2 guys and merge them, right? So you can right now end up with an array of like what, 3, 5, 7, and 9, right? Right now you have an array of this stuff, and then you have uh 2, 4, 6, and 8, right? And then you merge these 2 guys. Which is going to be, I don't know, was it like 2, 4, 5, 6, 7, 8, 9? Okay, so this is actually a nice sequence. So 2, 4, 5, 6, 7, 8, and 9, and you are done. This is how merge sort works. So,
Professor, what happened to 3?
did I forget 3? I
Yeah.
forgot 3. Yeah, sorry. Thank you for notifying me. So 3 and then 2. There we go. Yeah, I forgot 3. Thanks. Okay. And this is two-way merge sort. Now, the merging itself, is actually log n, because you are like reducing this thing like by half every time, right? I mean, if you go backwards, if you want to, right? So your problem is just simply like being reduced by half every time. However, the number of merges that happened when you are looping is actually n, because you are looping over every single element in there. Okay, so the actual complexity, when you're going to analyze the code later, when Adil will actually code it with you, it's going to be O of n log n. Okay, the problem with merge sort here is it's actually memory hungry, because you need to allocate lists all the time. Okay, so it really depends on your use case here. If you don't have a problem with memory transactions, like allocating memories and stuff, then you shouldn't actually be having an issue here. but it's actually like but it's actually quite fast. It's actually good, not bad of an algorithm at all. Yeah, and I think this is it, pretty much it. There's nothing more fancy about merge sort other than that. And it's a divide and conquer. You divide your problem into multiple pieces, and then you conquer them piece by piece, and then you resolve the problem in that way. Are there any questions, by the way, regarding this? Okay, well, if there's none, I will move on with quicksort. Quicksort is one of these interesting algorithms, which are, I mean, it's actually very fast. Surprisingly enough, it's made by a guy. His name is Thomas Hoare, I think. So, in the 1950s, actually. His name is written like this. I think there is no E at the end. And he was actually like he developed it over several times. Like it's a variation over shell sort. So you have an algorithm called shell sort. It's a variation of it. And it's actually like even shell sort is at a certain point in time. If you, I mean, we are not covering it here, but shell sort at a certain point in time, like at the end of the steps, it becomes an insertion sort. It has, I think, it has a best case of it has a best case of, I don't know, I cannot remember anymore. N, not n log n, but something a little bit slightly higher. But it was actually the fastest known algorithm at the time, before Tom came in and he actually he had to like sort data on a magnetic tape for faster access. And magnetic tapes are usually like they're like relatively sequential. It's easy to access data in sequence, so it would be best that they are sorted. So yeah, and it's also a divide and conquer algorithm, and you're gonna see how it works. So assume that you have an array that looks like this. 10, 16, 8, 12, 15, 6, 3, 9, 5. Okay. And it's actually in place sorting. Like you don't need to allocate arrays. You don't need to allocate any memory. You just simply use it right away. Now there's one more concept like you need to understand that what quicksort needs to do is to divide the array into two pieces at a certain point in the array. Everything, and like for example, let's say you would like to divide the array by half, for example. So you say if this number is here, your objective is everything on this side is less than this number, and everything on that side is larger than that number. That number is called a pivot, and it's written like this. Okay, and a pivot is something like a, you can think of it like something you articulate on, right? It's ako hoćeš da rotiraš objekat oko tačka neka, tvoj lakat je nekako sličan pivot, ajmo reći tako. Maybe we can think of it that way. If you think of your elbow as a point, and when you rotate your arm around that point, or not the forearm, but the other part, like where the hand is, right? So you try to rotate that, you are actually rotating around a certain pivot point. And this pivot point is your elbow, let's say, okay? I mean, I'm trying to give an example here, but I don't know how it can be translated. But hopefully you get the idea. So this is what we are trying to do. Get a pivot, try to find a pivot point. And when we say everything on the left side is less and everything on the right side is more. And that's pretty much it. This is the objective. Now, obviously, choosing a pivot is a very interesting problem, because you don't know where the pivot is going to be. You don't know where to put it, right? Which number can be the pivot? I'm going to actually use a very Blackboard friendly way of doing this, and then I'm going to talk about choosing a pivot later, and you will see how it will actually work. And once we are done with that, we can wrap up. Okay, so let me erase this. So we're going to have a J, and we're going to have I. In fact, J is not even pointing to 5. J is actually pointing to infinity somewhere. It's just standing somewhere out. And I is actually pointing to 10. Okay? So, and I will choose 10 actually to be my pivot for now. But right now we won't think about this for a minute. But usually we can say, because this is a Blackboard friendly explanation, I'm going to say that this is going to be my pivot. But keep it on the side for now. Now, how can I actually, what is the I, what is the J? So J is going to find all the numbers that are less than the pivot. And I will find all the numbers that are more than the pivot. And that's pretty much it. This is your objective for now. Once you satisfy the condition, you swap. Okay, so let's see. The first step is going to be increment the I. So is I, or is 16 is larger than 10? It is. So let me actually write here down. So I'm actually trying to find if I is larger than 10. So it has to be true. This is my condition. And J has to be less than 10. Has to be true. So true. Okay? This is my objective. Whatever J is pointing at, like, right? So this is the indexing. I'm talking about the indexing part. Okay? So we're going to decrement J here. All right? Because we found the number, we stop. So is 16 larger than 10? It is. We stop here. Let's decrement J. Is J, or this 5 is less than 10? It is. We stop J. We swap. So you swap these two numbers. So right now you're going to end up with an array which looks like 10, 5, 8, 12, 15, 6, 3, 9, and 16. Okay? J is still here. I is still here. Right? And this is still our pivot. Okay? Which we compare against. All right. So we move on. Is I larger than 10 here? It isn't, right? We move on. So we move here. I, so I plus plus. So this is I is larger than 10? Nope. Move on. Is this part is larger than 10? It is. We stop it. Let's move here. Is J is less than 10? It is. We swap. So you swap these two guys. So right now you end up with an array that looks like this: 10, 5, 8, 9, 15, 6, 3, 12, and 16. Maybe I shouldn't make it so close. Hang on. Let me actually try to see if I can pull this away a bit, like so. Okay. I is still here. Ah. I is still here. J still here. We move on. Is 15 larger than 10? It is. So we put I. So we actually put the I here. So since 15 is larger than 10 and is true, we stop. Whoa. Okay, I don't know why the heck did this turn on. Okay, we move on J, so we move J to the side. Is J less than 10? It is. So we stop it, and then we swap. So we swap this guy with this guy. So at the end of the day, we end up with, let me write it down here a little bit farther. So 10, 5, 8, 9, 3, 6, 15, 12, 16. Okay. I is still here. J still here. Okay. We carry on. Is this guy, so we move I. This guy is not larger than 10, so we move it. 15 is larger than 10, we stop it. So I and J actually right now are here. Okay. Now, since 15 is larger than 10, we stop the I. Now, what you do, you move J, right? Because we said we decrement J to find the least one. So here J is going to be right here. The moment I and J crosses each other in that way, we actually stop. And then you swap J with the pivot, because this is the pivot all the time, right? So this is pivot, this is your pivot, right? And then you swap J with the pivot. So we take this guy, so 6 and 10, and you swap it. So right now we have 10, sorry, 6, 5, 8, 9, 3, 10, and then 15, 12, 16. Hopefully I didn't forget any numbers. Nope. And right now, this 10 is actually sorted. So right now, the whole array is divided into two pieces. Whatever is in this side is larger than 10. Whatever in this side is less than 10. And what is the next step? You're going to actually ignore 10. You grab this array, and you grab this part of the array, and you start resolving them. So right now you pick this guy as a pivot, for example. Here's your I, here's your J, and then you work your way out. Once you are done, you pick up this guy. Here's your I, here's your J, here's your pivot, and you work your way through. This is why it's a divide and conquer. You look the first tackling of the problem, you actually look at the algorithm. You look at the array, the full array. You find the pivot, like you sort the actual number, you find the sorted position, and then you actually swap things out. Once you divide the array using that pivot, you start actually attacking the other two. And right now, for example, once you actually sort this guy, for example, you're gonna get one number here. I'm not saying that this is the number, but one number here will be sorted. And then you're going to have an array of two elements here and an array of two elements here, which you're going to just simply sort them. So it's actually easy, right? It's actually very, very fast algorithm. In fact, it is O of n log n. Now, here's the interesting question. Like statistically, it is super fast and it doesn't allocate memory. By the way, it is really, really fast. The question here is like, what is the worst case of this algorithm? The worst case of this algorithm is O of n squared. And it's going to be O of n squared because if you have a sorted array and you choose your pivot to be your first element, there are many researches, by the way, in how to choose that pivot. Now, using the pivot as the first element in the array is always a bad idea when in quicksort, almost always. Okay, I'm using it here because it was a Blackboard friendly, but if you are actually using this, there are I think in the books, so in the white book, data structures analysis, data structures and algorithmic analysis in C, they mention like I think 3 or 4 techniques on how to choose the pivot. So there are many ways of choosing a pivot. One is to choose randomly in the list. Choose one element in the list and say this is the pivot, and then you start doing the algorithm. You compare against it. You have statistically, you have a better chance of getting away from this and getting closer to this. You have some people actually say choose the median value of a list. So find the median number, or a statistical analysis, like you find the median in this list. And once you choose the median, this is actually your pivot. But this requires a search, which is okay. This is one way of choosing a pivot. And what was else as well? Like, I don't know, like there is also 3 pivot system or something like that. But again, there are many ways to figure this thing out. What I mean here is if you are implementing it by hand for any reason, you usually shouldn't, if we are talking about efficiency, you usually shouldn't pick up the pivot to be your first element. Do you have any questions regarding this? I mean, actually, like this, the other steps is you only need to continue it. There's nothing very fancy about this. Right now, you can just simply like carry on with this by hand if you want to. I'm gonna actually stop recording here.